My name's Howie Speeden. I'm a senior applications engineer here in ATS Life Science Chicago. This is a traditional, what we call a tube set assembly machine, where we start out pulling the length of tube, loading the tube into this over and under chassis. And then as we progress down, we'll work on one side of the tube where we'll apply an adhesive or a solvent. We'll load the fitting or assemble the fitting. We'll verify that we've done this successfully. If so, then we'll process the opposite side of the tube, once again, assuring critical quality. And then at the end, we'll ultimately either reject all components identified as unacceptable, or in this case, we're unloading the accepted units into a bulk container. Here we start on the beginning of the process where we're acquiring a tube, we're pulling it a certain length, separating it, and then we actually load it into the what we call the indexing chassis. And you'll notice that after the tube is placed, that we have the tube ends extending over freely within the transfer. Years ago, we used to use a razor blade for separating the tube. Well, here we've used technology that we've implemented, but we're separating the tube with ultrasonics. The benefit of this is, one, extended wear life, but more importantly, significantly reduces the risk of any particulate getting in the ID of the tube. The tube is loaded into the over and under chassis with the ends slightly overhanging. We actually are acquiring or positioning the tube end, if you will. In parallel, we're acquiring the fitting that's being introduced via vibratory feeder. We bring that fitting up to the center tube end, and then everything pauses. And we actually dispense the solvent, allowing the solvent to wick around the tube end. We retract the dispense valve, and then we actually take the fitting in, we insert it, we retract it, and then we give it a full insert. And what this does, this just ensures that we have full coverage of the bond. Some of the challenge with this station and how we overcome it, handling a tube, it's like handling a spaghetti string. It's loose, it's not stiff, there's no column strength. So it's coming up with the proper geometry that you could actually acquire the tube and center it. The next challenge is applying the proper amount of solvent. If we dispense too little, we don't have proper coverage, we won't get a full insertion. We dispense too much, then solvent migrates on the tube, causing what they call a fracture, or worse yet, it could actually cause an occlusion. And then the third one, we're running at the speeds that we're looking at on this machine, is just the feeding the components in that rate. In terms of centering the tube, that's actually just a culmination of years of designing the technology and optimizing it, making sure our movements are synchronized properly with the insertion of the fitting. In terms of applying the solvent, a lot of it has to do with the timing, and it's engineered, or that's established during the engineering phase. We know exactly where all the components are within 360 degrees of the cycle. And then in terms of bringing the fittings in, handling the fittings, that's just applying a lot of lessons learned to make sure we don't repeat mistakes that maybe we've made in the past. Some of the newer technologies that we deploy here, with the advent of linear motion technology and our ability to integrate it within the synchronous technology world, it just gives us ultimate flexibility in terms of fine-tuning the machine. After we insert the fitting, we're actually verifying that we have a complete insertion. Years ago, we used to do this with maybe rudimentary photoelectric sensors, and we didn't quite get the granularity that the industry really expects from equipment these days. So now, with the advancement of vision or optic technologies, we can confidently and provide a robust solution for inspecting customers' product. The future trends that I project, when you get into solvents, a very efficient and cost-effective way for bonding one part onto another. I mean, we're basically melting the plastic together so we get that sealed joint. But the reality is, some of the solvents, they're not the friendliest to use. There's often safety requirements that we have to deploy on the machine. And then you always have the disposability, which may not be easy for some of these chemicals. I predict, and I know there's actually in the work, that there's going to be technologies that will actually eliminate the use of the solvent, and we're really excited about it. Because we've integrated the newer technology, specifically linear motion, now we have a significant controls engineering element in there. And I've already mentioned the critical to quality inspection. Now we need vision engineers that actually participate in the team. And because this is a medical device, once our customer takes ownership, he has a whole validation process he has to go through. In ATS, we offer a validation package that the customer can reliably acquire, execute the protocols, and it's something that they can, with confidence, present to the FDA. So it's not only just the mechanical engineering, but you'll have the controls engineering, you have validation. Of course, you have a supply chain that's involved. There's a lot of little pieces. There's third-party components, for example. So in terms of sustainability or the environmental goals, our customer has very high expectation on performance. So when we think about the scrap that's product that just goes from the machine to the landfill, it's just a very low occurrence only because the machine performed at high levels. Secondly, it's just controlling the solvent. A lot of our design support not wasting, only using the solvent that we need. One of the aspects that I'm really proud of on this equipment is, for the longest time, we thought that there was a max threshold of what our machines could produce. In other words, the parts per minute. So in this machine, the customer challenges, they just said, we need more parts per minute. We can't use a lot more floor space. So the team really stepped up to the challenge, and using, or integrating, I should say, modern technology or linear motion, we were actually able to increase the throughput of the machine by 30%.